How's everyone doing tonight? Good. Weekend's coming up. So this will be our transition point. I have started scoring the exams. I looked at the first 6 multiple choice questions. I'm doing something. I'll post before Tuesday night. I'll post the solutions that I came up with. On the multiple choice, I tried something a little different. There was a couple questions, or couple answers that were close to, that if you made one mistake, you might go that route. So I sort of weighed, if you chose that one, it was worth 2 or 3. One of them, it was worth 4 points because there was just one difference. So you either got 5 for the right answer or 4 for the alternate answer. So you'll see that. The thing that's not too many people are putting in the alternate answer, so it's just kind of like either right or wrong. So, and a couple of them I have basically 2. So there was 3 of the 5 answers you would have at least got some points for. Okay, so I'm doing that, and then I'll keep going through. There was some debate on the true-false by the professors about the last question is there an absolute minimum? So that may be something. I know it was coming up here, and I said just look at the graph. They decided to give everyone 2 points because the intention was that there is no minimum because it goes down to negative infinity. Negative infinity is not a minimum value. But if some of the homework ones, they don't say that the domain's limited, so it was ambiguous. So there was 2 against 2 for, so yes.
Adam, the scores that you've seen so far, is it around the same as last quiz?
I haven't gotten far enough because I haven't even started looking at the others. So I'm just looking at the first 30 points. And so, yeah. So I'll do that, but then I'll also remember I gave a test in my pre-calc. They're completely multiple choice. So I got those to grade, and then I gave one at my community college class. So I'll be grading a lot. Yeah, so I know. Here's the thing, though. I'll have them certainly posted over the weekend. I will have them ready to hand back to you Tuesday in class. So, and again, those that aren't here, if we're recording this, hopefully they're watching this. If you want your test back, the best way is to come to class to get it. Because after that, I don't bring it with me regularly. So then, you can still get it. Just come to office hours or let me know and I'll bring it. But Tuesday, we'll hand them back. I believe the last day to withdraw for this semester is April 2nd, someone was saying. Is that about right?
Yeah.
Okay, so we'll have, here's my you've come this far, why not stick it out? If you don't finish it, you're going to have to retake it anyway, right? Most likely, unless you're going to change your major, but I mean that happens. But if you're going to have to retake it anyway, my suggestion is to keep going through to the end. Because here's what I'll do is I do have the syllabus, so whatever's in there, that's, you can count on that. If you've got an A based on that, you've got an A. The other thing I do, though, is I look for improvement. So I'm going to heavily take a good look at that final exam. So as long as you can, maybe the lights will start clicking. And a lot of times, this stuff we're going to look at tonight is where if it wasn't clicking, sometimes all of a sudden everything makes sense because we're doing everything backwards. And so now the earlier stuff actually makes better sense. So you're going to do better on the final. And so my promise to you is if you pass the final, you will definitely pass the class, regardless of points. I can adjust it that way. More than that, if I see significant, it could, and I'm not saying, well, you got C on this. And I also don't believe in penalizing you for the struggle part. So just because you didn't do well at the beginning, it's that you did well at the end. So, well, I won't give specific details because I do kind of look at that and put everything together. But if you stick with it, as long as you can get a passing grade on the final, you will pass the class. Okay, so we'll put it that way. And I think by the time we get to test 3, you'll be doing well. Okay. And I know it gets this is for the business school. This is a specific class that a lot of them look at. So there is a lot of stress. I was contacted by a few that were kind of a little bit stressed out. I I said, well, you still have to take the test, right? So keep doing the best you can, and even if you weren't fully prepared for this one, again, we've got this time till the end. In fact, let's go ahead and take a look at our schedule. So I added this content for test 3 now, and we'll take a look at that. The other thing I'm kind of thinking in circles, I added the practice test that I didn't have anyone do, but I assumed that you all worked through the study guide to get ready for the test. So I gave everyone 50 points for a practice test. So that was just put in recently, like 30 minutes ago. If you didn't do any studying for it, let me know. But if you didn't study for the test, I don't see how you could do very well. Or if you did well, then you probably didn't need to. So I'm not worried about it. But I was a little bit behind on putting a practice test. But I think the practice study guides that we have are really the best preparation. So I want to focus on those. So we don't have too much time. So we've got really just 2 full weeks, 2.5 weeks, and then we're into review again. So because what we're looking at now is not really anything new. We're just doing the same thing, but we're now doing it backwards. Okay. And again, that sometimes is helpful in understanding things, but because it's backwards, it's also easy to get a little bit mixed up. And there are, I'm not saying it's easy, but I think you're going to find the learning will come a little bit quicker. Okay. So let's go ahead. Let's see, let me get my, here it is, okay. There it is. So this is what we're going to we call it the integral. And briefly what it is the difference geometrically, when we got the derivative, remember what is the derivative? What's the geometric representation of a derivative? Tangent line, specifically the slope of the tangent line of a curve. So that's how we got those. So that's the slope of the tangent line. That's a derivative. Geometrically, what the integral is going to be, it's the area under a curve. And what it technically really is, it's the area under the derivative curve. So here's the 2 places we use this. We use derivatives when we have a good function for the value, like our profit. We've got data on our profit. We can get a function for it. We take the derivative so we can see where we're going. What we use the integral for is if our data consists of stuff that's rates. So we might not have all the profit, but we might have all the data on how the profit is changing, right? Rate of change. And so if that's our data, we use the integral to get back to what a profit function would be. So we take the derivative and turn it back into the function. So that's what we're doing. Is we're starting with the derivative now, and we're working backwards to get a function that would give us a value. Does that kind of make sense? Okay, so that's really the 2 parts of calculus. So we're going to start off with what we call the indefinite integral, which means, I'm not really sure why they call it the indefinite, but it'll make more sense when we get to the definite. The definite would basically, we put boundaries on it, so there's a specific area under the curve. The indefinite, there's no boundaries, so it's just kind of, we're looking for the formula. So but it never makes sense at the beginning. We also call what we're doing an antiderivative, right? Because we're starting with a derivative and we're underivatizing it. It's just a word I made up, but so we're undoing the derivative, antiderivatives. So what I want to start with is a few things. Let's talk about what we're familiar with. So if I have a function, y equals, let's just make it pretty simple, x to the 3rd plus 5. So let's say that's some kind of value function, and I want to get its derivative, right? How do I do that?
Equals 3x to the 2.
So the 3 comes down, so let me diagram this. The first thing we do is we take the 3 down in front and make it into multiplication. So that's the first. Because this is what, remember, when we go backwards, we also do everything in reverse order. So what we do first here is what we're going to do second. And then the second thing we did when we took the derivative is we subtracted 1, right? So this was the second thing we did. So that gave us x, go back here, squared. And when we took the derivative of a constant, we got 0. I'm going to emphasize that with a plus 0. Okay. We typically were calling this y prime, but there was another way we could have written it, right? We could have written it as dy dx. And that's the notation I'm going to start using, because we're going to see with derivatives, or sorry, with integrals, we use this dx part a lot. Okay, so is that okay? That's just a derivative, right? So the derivative of y, we did this dy dx thing when we were doing implicit derivatives. So it's kind of like taking the derivative of y is dy dx, derivative on the other side, 3x squared plus 0. Okay, so what I'm going to do is, when we want to start talking about an integral or an antiderivative, what we do is, could we just like multiply both sides by dx? Right, dx divided by dx, treat it like a fraction. Not sure that that's completely kosher to math folks, but it works. So it works, and conceptually it fits in there. So that gives us dy equals 3x squared. We'll get rid of that 0 because we don't need it, dx. So does that make sense? That when we look at this, we can see, oh, we got a dy and a dx, so it's a derivative thing. It's a rate of that. So what we're going to do now, so that's what we've been doing. Again, we might not have split it like this, but what we're going to do now is, in this form, we're going to basically, if this are equal, because we took the derivative and we just sort of multiply both sides by x, we can do, as long as we do the same thing to both sides, right, it's going to stay the same. So we're going to introduce something called an integral, and this is a symbol for an integral. It's sort of an S shape because it's really a sum of areas underneath the curve. I don't think we get that deep into it, but that's exactly what we're doing. So we're getting area under a curve, and so that S is for the sum of all those little regions that they take. So we're going to take the integral of both sides. And again, the PowerPoint kind of walks through this, but I want to just kind of give a preview of it, and then as we actually start talking about it formally, it should hopefully make more sense. So we'll call this the integral. And what we're supposed to end up with, and this is because I wanted to show this middle step, we're supposed to end up with what we started with. Okay? So would it make sense that the integral of dy should just be y? Good, because it is. It is. So as I integrate dy, I get just y. Okay? And that's going to match up with what I had up here. So that's good. And then when I integrate 3x squared, I can do exactly the same thing I did when I took the derivative, but I'm going to do inverses and in the reverse order. Okay, so now I've got 3x squared. So what did we do first? We multiplied, and then we subtracted 1. So what's the second thing? We subtracted 1. What's the inverse of subtraction? Addition. So what we're going to do is we are going to add 1. Make sense? We add 1, 2 plus 1 is 3, and that's what we started with. Oh, this is looking good, looking good. And then, again, the first step we did was we multiplied by 3, right? Well, let's put it more accurately. We multiplied by the exponent, right? So now the second step would be to take that new exponent, right? 2 plus 1, and not multiply, but divide. Okay, so now I'm going to put this as division 2 plus 1, just to show that that first step was to add the 1, and now we're dividing by the new exponent, and what do we get? we get 3 divided by 3, x to the third power. So that can't, we get x to the third. Isn't that what we had? Oh, but we're missing something. Plus 5. But just looking at this stuff that we got down here, how would we ever know it's going to be 5? We don't know. It could be, it could have been 27. It could have been anything. This constant could have been anything, and when you take the derivative of constant, it's always going to be 0. So here's the cool part. We can just say, well, I don't know. It's a c. It's a constant. So what we get is we don't get the specific function. We get a family of functions. And we could, yeah, plus 5 is one of them, but again, there's no way to figure out the plus 5 unless we had more information. Some of the problems, they'll give us some initial values.
Could you just plug that function into a calculator and then look at the table to see where it's for that constant?
You mean this one?
Yeah.
Probably, yeah, because actually calculators do have a way of taking an integral. So they could, yeah, technology's beautiful. It does a lot of stuff for us. But it's also gonna, because unless we have additional information, it still wouldn't know about the 5 with just, if we gave it this. But yes, it would get us to this, definitely. And that's one of the things, those CAS calculators, they'll actually even do it all symbolically. So they're like a little symbolic, that's why they don't let them be used. I figure if you're smart enough to figure out how to use those things, you probably, I mean, it's like you almost need a separate degree to use, anyway, yeah. Okay, so this is what we're going to be doing, just kind of, instead of subtracting 1, we're going to add 1. Instead of multiplying, we're going to divide. And we do it in the opposite order. And then there's just going to be a few special cases, like when we have logarithms, right? That works differently. So we'll talk about those. Those are not too bad. That we'll be able to identify when we've got an integral that's going to become a logarithm. And the other one was exponentials. Those behave differently as well. But any polynomials with something with an exponent, we just add 1 to the exponent and divide. Okay, so we're going to see. And the cool part is then when we're done, we can take this derivative if we take this derivative, we're back here. So it's kind of like this. We have a way of checking for the most part. Do it, and then take its derivative. Oh, I got back to where I started, so this must be it. But, the homework will typically, sometimes they just hardwire in a plus c, but then sometimes they expect you to put that in. That was one of the things I'd always forget, because I was so busy on taking the integral, I forget about that plus c, but it's always there. Okay, that's the lesson for tonight. So we're done. No, not. So now we're going to do the formalized stuff, but that's it. That's really pretty much it. Okay, we'll talk specifically about logarithms, but they're actually not so bad with what we're going to do. So here's our example. And they just go boldly and say, well, if I have 4x to the third, its antiderivative would be x to the fourth, because if I take the derivative of x to the fourth, I get 4x to the third. So that's just their way is we can go, that's all it is. Antiderivative is what I had before I took the derivative, right? So, and then they're kind of going to, take some time to give us some definitions. We call this the indefinite integral. And they basically telling us we get the set of all antiderivatives. So in a second, they're going to show us about the plus c. So there's multiple families of stuff. So, and I don't know, this for me is a little hard. They now use sort of the antiderivative function is big F, so that when you take the derivative of big F, you get back to what you started with. But if you just say that we've got two things and we're starting with the derivative, when we take its antiderivative, we get back to what do we get? Now see, I get confused. We get back to the original function, right? So we've got a derivative, we're trying to get back to what it was before it was someone took the derivative of it. And then the notation is, we get with it. So then they introduce this little symbol here, the integral symbol. And again, it's sort of like an S because it's for the sum of the areas, and that's really what we're getting let's see. And again, it's just kind of wordy, but again, the key part is a collection of functions, and so they introduce it down here because a constant, when you take its derivative, is 0. That part's going to disappear, so we always, that number could be anything. And again, what they will have to do is give us some, we'll do a couple examples. I think in the homework there's maybe 1 or 2 at the end, where once you've got the the integral, you take the initial value stuff, you can plug that in and you can solve for what C is in some cases, if they give you that information. Okay, and C is called the constant of integration because it's the original function. It's anything, if it had a constant, it becomes 0, so there's just a possibility. C could be 0. So it's a possibility. So far, we doing okay? Okay. So here's some quick examples. So if I'm going to integrate x to the 1 power, right? 1 plus 1 is 2. There it is. And then I've got to divide by that 2 because if I take x squared and I take its derivative, the 2 is going to come down, but there is no 2 here, so that's why I'm always having to divide by the new exponent, right? We'll go through here. X squared, right? I add 1 to the exponent, I'm going to get x to the 3rd, but I've got to divide by that 3 because if I don't, when I take the derivative of x3, I get 3x squared, and notice the integral doesn't have that 3 there, so it's just kind of, you know, all the steps. And this is the one they threw in there. If I've got x to the negative 1, remember, you might think of it as 1 over x, which is a better way. That is a special one, because what if you, in the way I remember this is because let's just pretend that it's a regular thing. I got negative 1. If I add 1 to negative 1, what do I get? I get x to the 0, which is 1. But if I take the derivative of 1, which is a constant, I get 0. That doesn't work, right? I don't get back to where I started. So it's kind of like, this is a safe one because if you don't remember, it doesn't work like all the other polynomial stuff, right? It's a special case. Oh yeah, this guy. This comes from natural log of x, because when I take the natural log of x, I get 1 over x. So it's just that special case. It's one of the ones we did at the end. So whenever I got x to the minus 1, remember, you're just going to get natural log of that thing. Okay. And I don't think there was that many. There's maybe 1 or 2 in the homework. Again, it will come with time. These ones are all pretty straightforward. Just add 1 to the exponent, divide by the new exponent. And the PowerPoint kind of goes through and checks, you know, yeah, if we do that, we end up with this, which is x, which is what we started with. So if we take the derivative of x squared over 2, we end up back where we started. This one, if we take x to the 3rd over 3, which is when we integrated, that's what we got. If we take its derivative, we end up back at x squared, which was what we started with. So that's what I mean. You can once you integrate something, you can always check it by taking its derivative. And natural log, yeah, if you take the derivative of natural log, they use the absolute value because of the domain of the natural log. You can't have 0 or negatives, right? It's undefined there, so they just put that absolute value there, and we get that. So calculating indefinite integrals. So we're already up and running. So again, here's now they're going to define it. So we add 1 to the exponent. That's the first step. And then we divide by that new exponent, just like we did in that first example. Nothing special, nothing new. And then there's always that plus c, because a constant, when we take its derivative, is 0. Okay, so that's that constant of integration. And then there's the one special case if it's x to the negative 1, or like they have down here, this equivalent form 1 over x, that's that special case, that's natural log. Okay, it's just that, because again, if you try to do it with the add 1 to the exponent, you don't get anything that makes any sense. So this is the one that goes that route. Okay. And most of the homework, in fact, we could take a look at a few of them, but it's just going to be, here's a function, integrate it. And again, you're going to pretty much be adding 1 and dividing by the new exponent. Okay, so here's a quick example. So, and again, some of these, I've got a few where I cut them off, but it's just they're taking 55, you're going to add 1 to it, so you get 56, and you divide by that new exponent, right? Because we have to, because if we take x to the 56th over 56, and we take its derivative, subtract 1, we get x to, well, we would take the 56 down. Oh, and there's a 56 here, so that's going to cancel. And we subtract 1 from the exponent, that's going to be 55. Oh, x to the 5th, that is what we started with. So we'll be able to go back and forth. And so some of it is, you're kind of guessing, okay, if I took its derivative, that's what I end up with. Makes sense? Kind of? Okay. Exponential function. So this is the other special case. But before we go too far, what's the derivative of e to the x? E to the x. So it's kind of, and then remember, what is the derivative of, if we have some other base, let's go with 4. 4 to the x. What would the derivative of 4 to the x be? I'll just do it this way. It would be 4 to the x times natural log of 4. So any other base other than e. Actually, e is also times the natural log of e, but the natural log of e is 1. Okay, so it's not really a special case. It's just that we skip over it so quickly. Okay, so an exponential is itself times the natural log of the base. That's what the derivative is. So if we're going backwards, what do you think we're going to need to do? We're going to have to copy it, and we're going to have to divide by that natural log of the base. Because when we take that derivative, it comes off, and we got to have something to divide it out. So e to the x is e to the x plus c. And again, we're sort of dividing by natural log of e, but natural log of e is 1, so it just disappears anyway. But you could think of it, that's really what we're doing. So if b is anything other than e, yes, its integral is just what we started with, b to the x. But since b is some other number, it's not e, it's maybe 4 like we did, we have to divide by the natural log of b, because when we take its derivative, that's got to divide it out because it doesn't have a natural log of b here. Does that make sense? Kind of. So it's just a special case if we're having if we're integrating an exponential. But again, in business situations, a lot of times you are going to be using e. You know, it comes up a lot in finance. So, and again, they've got the examples over here. Let's take the derivative. This part cancels out, and we're back to where we started. Okay, so you can always go back in a circle now. Okay, now we're experts, sort of. Okay, what if we had something more than just like x squared or x to the 4th? What if it's x squared plus 2x, and if there's more things, then just like we were doing with derivatives, we break it up by term. We really can just integrate each term as it is. So when we've got, and we'll do a few of these where there's this plus that minus this. We just break it into multiple state. If it's a trinomial with 3 terms, we integrate 3 separate things, and then at the end we end up adding or subtracting them as the case may be. Okay, so the integral of a sum is a sum of the integrals. So it all works out. Again, in this class we're not going to take the time to do proofs. It does work. I remember when I was doing this as a math major, I spent about a week on this first part, and you look at all these proofs that don't really help you do it, but they just let you know you can. And I said, well, if it's in the book, it must be somebody figured it out, right? Also, another thing we can do, if there is a constant, some kind of constant, right, a constant multiplier. Remember when we were taking derivatives, that constant multiplier just tagged along for the ride, as it were. So when we're taking the integral, we can say, well, it's just going to tag along, so let's just move it outside and not even deal with it. we'll take the integral, and at the end we'll multiply by whatever that number is. So it makes it a little easier. So if we had something like the integral of 5x to the 9th, right? What do I do with this 5? Well, just move it outside, and let's just focus on x to the 9th. How do I take the integral of x to the 9th? First step, add 1 to the exponent. Second step, so I'm going to get x to the 10th, is divide by that new exponent. And then I just, oh, there's this 5 out here, let's just multiply by 5. And then you could figure, you know, but sometimes if that 5's there, you're trying to put it in and you're trying to figure out what am I supposed to divide by so that I, you know, you don't have to worry about that. Just go ahead and take the integral over here and then multiply by that constant multiplier. Okay. Oh, they even said, that's where, maybe that's where I get it, goes along for the ride. That's what my teacher told me 30 years ago. Makes sense. So the sum rule, if we've got two terms, we just break them up into two integrals. Integral of x to the 3rd is going to be x to the 4th over 4. And here's this one that I guess we didn't talk about, but what is this x, you know, what is 1? It's really the integral of x to the 0, right? So this is a way we can think of it. Add 1 to the exponent, divide by that new exponent, so it's going to be x to the 1 divided by 1, which is just x. Okay? So yeah, when we're integrating just 1 dx, it's just going to be x. And because, right, if we take the derivative of x, we get just 1, the number in front. Okay. Constant multiple, I went through it, but they kind of, okay, so take the 5, just put it on the outside, do our work on just x to the 3rd, there's that, and then combine it at the end, so 5 times that. So 5/4 x to the 4th. Okay, plus the constant. Okay, applications. So we're already to this. So we're going to take a look at a couple of these, especially the second one is dealing with falling objects. And let's see if we can remember this. If I have the position function and I take its derivative, what do I get? Position gives like distance traveled or something. I take its derivative, it gives the rate of travel over time, which we call, not quite, what's that? Velocity, directed, or speed. When I take the derivative of velocity, then I get acceleration. So those are the 3 places. Acceleration is how fast is the speed changing. The velocity is directed speed, and the position is just basically distance traveled over time. So we've got position, velocity, acceleration. So what are we going to do in this class, or this part of the class? We're going to start with acceleration. We'll be able to get back, integrate to velocity. Once we've got that, we can integrate velocity and get back to the position function. Okay, so yes?
And the constant is just being where it started?
Yes. Well, they'll give us enough information to kind of figure that one out too. The thing is a lot of times what they're going to do is when they're using these position functions, you know, something being thrown up in the air, and so if we throw something up in the air, what happens to it? At least it comes back down, right? Even if you shoot a gun in the air, the bullet, it will come back down. So that's why it's not really a good idea to just shoot in the air, because it will come back down and maybe, you know. And what causes it to come back down? Something called gravity. And on this planet, pretty much, I mean, there's a little differences, but there's a constant of acceleration. So we're going to talk about that, and we'll sort of derive it. Okay, so here's a business application. We've got a marginal cost. What is a marginal cost? It's what?
The cost to produce one more.
The cost to produce one more. So it's a rate. It's a derivative, right? It's the first derivative. So to get back to the cost, we're going to integrate it. Okay. So the marginal cost to produce production level of x caps is this function here. So marginal cost, so that's a derivative in our mind. That's what we're thinking. The cost of producing 100 caps is 500. So this is going to actually be the first time we're going to be able to solve for what the C is with this extra information. Find the cost function. So again, the PowerPoint in the next slides, they will work out the solution for us, but I thought let's just kind of see how we go. So we're going to start with this first one, right? We're going to take our derivative function. So it's dx, that's what, and we're going to integrate it. So we've got two pieces, right? So can't we just integrate 4 dx minus, and this 0.001, I could think of it as a constant multiplier. So is that okay? So just sort of algebra of rewriting the integral of these two terms as the integral of the separately the two terms. So thinking about this, what would be the integral of 4 dx? Four x, right? Because it's like 4x to the 0, add 1. This is just going to integrate into 4x. Okay, so when we've got a constant dx, it's always just that constant times x. So that's that one. If I integrate x to the first power, what do I get? Oh, not add 2, add 1. I'm going to end up with 2. See, I jump the gun sometimes. You add 2. I did it again. It's been a long day. Add 1. And then 1 plus 1 is 2, so we're going to divide by 2. So this becomes minus 0.001 x squared over 2, right? Plus a constant. So that is the antiderivative. That is the function we would have started with. We can test it out by taking its derivative. So derivative of 4x is just 4. Oh, that's good. Derivative of 0.001 x squared, well, this 2 comes down, divided by 2 goes away. It's just going to give us minus 0.001x. So you can kind of just mentally see that, hey, if I take its derivative, I got back to where I'm starting with. So now, beautiful. This is, what did they ask? Find the cost function. So this is the cost function. So again, if we had the marginal cost, we can now go back and we can actually now say exactly what it's going to cost. Remember, the marginal cost only would tell us the cost to produce the next one. But with this tool, we're able to actually get the function so that we could see total cost. And the only thing we're missing is this constant, which, that's our fixed cost, but we can figure it out because when x is 100, the cost is 500. So we come down here, we're going to plug in 100 for x. So what we know is C of 100 equals $500. So we know that it's going to be $500 4 times 100 minus 0.001 100 squared over 2 plus a constant. And notice oops, I guess I can't go up. So 4 times 100 is 400. Let's see, that's going to be, where's my calculator? It's going to be 0.001 times 100 squared, which I think is still 100. You got 10 for the total? Okay.
Well, I think it's negative 10, right?
Yeah. So it'll be negative 10 divided by 2, or did you already do that?
No, that was just for the top.
Oh, just the top part. Okay. So 0.001 times 100 squared, oops, 0.001. 10 there, and then we divide that by 2, so that should give us 5. So it looks like we get 395 over here. So 500 equals 395 plus a constant. So 500 minus 395, right? Looks like we've got fixed costs of $105. And so now we can actually write the full equation that our cost function is 4x minus, I guess, 0.001 divided by 2 is 0.0005 x squared plus 105. Yes.
I'm confused, so you don't plug in 500 for C when you're solving for that? You just set it equal to 500?
Well, the cost is 500, so C, the output is 500.
Okay.
Yeah, so the cost of the caps is this. So C of x, C of 100 equals 500. 100 goes in for x, 500 is the cost. I mean, okay. So this is where we can actually find the C. Good? Got one more example, which deals with gravity, which is going to be helpful for the last of the homework problems. Questions? Yes, sir.
Where did you get the, I must have missed it, the 4x minus 0.0005? Like, how did that?
Oh, I took 0.001 divided by 2.
And that gives you 0.005.
Yeah, and that'll give you 3 zeros. So think of this as 10, so half of 10 is 5, so it would be 0.0005. Okay. And again, you could walk through, the PowerPoint does all the pieces, and they end up with pretty much the same thing we did. Okay, so it's all, you don't have to look over my chicken scratching, but hopefully my chicken scratching was helpful to think about how we step through the process. So motion of a straight line. So here's where we talked about, again, we've got position, take its derivative, we get velocity, take the derivative velocity, we get acceleration. So we're going to think, so velocity is the derivative of the position function, ds dt. So it's how a particle is changing, the distance is changing over time. So it's the derivative of position. Okay, and again, this is just kind of going through. And then acceleration is the same type of deal. It's the derivative of velocity. So again, what we're doing is if they give us an acceleration, we can work backwards and get the velocity. Once we have the velocity, we can work backwards to get the position function. So now the way we're thinking of it is if I have a velocity, remember that's a derivative. If I integrate it, I get back to the position function. If I have the acceleration, if I integrate it, I get back to the velocity. So just like I could take two derivatives, I can basically do two integrals and get 2 steps back. Okay. So they just give us directly if the velocity were 4t plus 1, if we integrate that, let's go ahead and take a look. So we're going to integrate 4t plus 1 dt. So integrating t to the first, remember add 1 to the exponent, so that's going to be t squared divided by 2. The 4 tags along for the ride. When I integrate 1, what am I going to get? 1x or t is a variable we're using, so we use that. Plus, then we get a plus a constant. Okay, so that's what they did down here. They took 4 divided by 2, and they just wrote it as 2t squared. Okay, but notice I kind of bring things along for the right as we're going, and just add 1 to the exponent, divide by that new exponent. That's all we're doing. Okay, so now what do we have? Well, if this was velocity, we now have a position function. So we can say after this much time, this is how high the particle is or how far it is, depending upon what the units are giving us. So again, we kind of just walked through this part here. We integrated that already. We came up with, right, we'll just step through it real quick. So we end up with 4t squared over 2 plus t plus a constant. And then they tell us, so this is now, because this was velocity. And so the position function is the integral of that. And what we can do is, now that we know that the output S will be 2 whenever t is 1. So just like the last one, we come here, S of 1 equals 2. So for the S, the output, we put 2. I'm going to take this 4 divided by 2 and just write it as 2. T squared, well, t is 1. T is 1. And C is just C. And so we can do the math. We get 2 equals 2 plus 1 plus C. 2 plus 1 is 3. And then subtract 3 from both sides. We get that the constant is negative 1. So the position function will tell us S of t is 2t squared plus t minus 1. Okay. So if I put in t equals 0, I get that we're at negative 1. So maybe it's starting in the ground, or depends on what that, if it's height or whether it's distance. Okay. And then they do the same thing. And notice they ended up with the same answer. So these are just showing all the steps kind of printed out. But for me, it's hard for me to follow along something that's already written. I don't know about you, but maybe sometimes it's hard to follow along with my writing. So I give you both. Okay. Now this last one is going to be very similar to what we did with, or what you're going to be asked to do with the homework. Okay. So a freely falling body experiencing no air resistance and 0 initial velocity, find an expression for the velocity v in terms of t of the time. And then what we've got is that somebody went out and measured that there is this, with no resistance, that a particle, something falling, accelerates at, and we're going to use the feet version rather than the metric, at 32 feet per second. So that's acceleration due to gravity. So that's something that's been measured. So if this is our acceleration, and it's a constant, that's the cool thing about our gravity. It doesn't, the acceleration, it speeds up as it comes down. The velocity changes, right? But the acceleration doesn't. Acceleration is a constant. So what we've got is our acceleration function is simply 32 feet per second. It's a constant, it's a number. How do we get the velocity? We integrate that with respect to time. Okay, so there's that dt. So what's 32? What would 32 integrate into? 32t. See, I told you, you're already experts, right? So this becomes just 32t. Again, plus a constant, because we've integrated, there might be something, and sometimes that constant could be 0, but sometimes we might have given it a push, so there's some initial velocity. But if we didn't, if we just drop something, so it had 0 initial, the c would be 0, then it's just going to be, its speed will be 32. So that's acceleration. Each second, it's picking up 32 more feet per second. So it does accelerate. We wanted the position function. What would we do? we could integrate this function, right? And so the position function, now it'd be nice if we had some more information. We will in the next step. But when we integrate this, we're going to get 32t squared, right? Because this is t to the first power. We're going to add 1 to that exponent. 32t squared. I forgot one thing. Which way does gravity work? Downward. So we should put a negative here because we think of going up as positive and coming down as negative. Now, it's not necessary. You could do it the other way. So we do get this. We get this. We get this. T squared divided by 2, right? Because I added 1 to the exponent. I have to divide by that new exponent. So we're going to get a minus 32 divided by 2. But before we get that, then we get a plus whatever when I integrate c. C is just a constant. It's just a number. When I integrate it, what am I going to get? C times t. So that whatever number that is, that's why it's good to have to figure it out. And then plus there's something with just a constant. So 32 divided by 2 is 16. So in algebra, you see this all the time when the particle has got negative 16t squared. That's the force of gravity. And now you've just derived it from knowing that 32 feet per second is the acceleration. Here we got it. Then we'd have plus some constant times t plus some other constant. So, and that would be our position function. So that could tell us how high it is. And basically we just did, actually we'll do it with some numbers in here, but this is the last homework problem. And then you look at it, yes? I put a little c0 to call it, or c naught, the beginning constant. This is that the two constants could very likely be different. It could be the same, but they're just different numbers. And we'll go ahead and go to the next example because in the next example they give us enough information to figure out what the constants are as we go. But that's the step we're going to go. So we're going to start with acceleration. We're going to integrate so we can get the velocity, put in our numbers so we can get those constants. We're going to integrate so we get the position function of something that we throw up in the air or throw down or drop. Okay. And so, yeah, they just talk you through it and walk you through it, just what we just did. They do this. So our velocity, minus 32 t feet per second. And since the initial was 0, the constant would be 0. But if you gave it if you either threw it up, it would have positive, or if you threw it down, it would have negative. So this is a good slide to call up because you're going to see this in general. So yeah, velocity will always be negative 32t plus some sort of constant, the initial velocity. And again, we use it. So if I throw it up in the air, that's a positive force, so that'll be plus. So if I throw it 2 feet per second, I'm going to add 2 to it. If I throw it downwards, then that's going to be subtracting. It's going to make it go down faster. And then the position, again, what we came up with, and notice they use different letters here for the different constants. Okay, but it's just kind of like, okay, if we know what the initial velocity is, I could just fill that in. If I know what the initial position is, somehow I'm on a bridge that's 50 feet above the ground or so. Okay, I'm starting 50 feet up, I'm throwing it up, and we can come up with these equations pretty easily. And the questions we're going to ask are in feet per second. It works also with the metric, but that's going to be in meters per second, right? So that's your constants change because you're in a different measurement system. Gravity's still the same, but how we measure it is different. So this is kind of like the last homework problem. You're going to throw something either up or down. This is a ball is thrown upward at 2 feet per second. So that's speed, right? And it's a positive. From a height of 200 feet, we're going to need to find the velocity and position after t seconds. So again, where we start is that all we really know is that acceleration is going to be a constant, the gravity. So we're going to integrate that. And that's going to give us that velocity is equal to negative 32t plus some constant. What we do know is that the initial velocity is 2 feet per second upwards. So this is at time 0, right? Whenever it didn't specifically say time 0, but that's at the start. So when t is 0, we know the velocity is going to be 2. So we know 2 equals negative 32 times 0 plus c. So c has to be 2, right? So that's why that initial velocity, it wipes out the gravity. So what we can say is the answer to this, our velocity function is negative 32t plus 2. And if you looked at that other formula, the previous page, initial velocity is upwards, so I'm going to have a plus 2. If I was throwing it downwards at 2 feet per second, what would change? This would be negative, right? So direction. Not a big deal. Now I can get my position function. So s of t is going to be the integral of negative 32t plus 2 dt. So now I integrate each of these. Negative 32t, remember that's t to the first, it's going to become negative 32t squared divided by 2. Integrate 2 is going to be 2t plus a constant. So that's my position function. And the way I get to find the constant here is we know initially at time 0, the ball is at 200 feet, because that's where I'm throwing. I'm on a bridge or something, or a ladder, whatever, pretty tall ladder. So what I get to do is I say, well, 200, 32 divided by 2 is negative 16, right? Initial time, so that's 0 squared, right, t squared, plus 2 times 0, because it's the initial, plus c, so c has to equal 200. So you'll get used to this once you see it. Oh, that's the starting, that's going to be the constant. So this is the first answer. Second answer is the position function, negative 16 t squared plus 2t plus 200. Now what you should do is go back and look at all your algebra classes and anything with the ball going up in the air. You'll see that, and now you know where that's all coming from. It was determined with calculus. Okay. And the last piece of the homework, they tell you that they're giving it a different. You're starting at a different height, different starting speed, so you'll come up with a slightly different equation, but you'll always have negative 16t squared because that's gravity. It doesn't, unless you go to the moon, that's not going to change, or someplace else. So on Earth, you're always going to see that negative 16t with something being thrown up or down, or shot up and down, whatever. I think that's, and then, oh, there's no more to it, so that's it. You see it's a Galileo, you're on the Leaning Tower of Pisa, you're throwing the ball, so, now you can do it all. Okay, but mostly it's like 16 problems, but it's just giving you some practice with taking integrals, adding 1 to the exponent, dividing by that new exponent. If you just that's your mantra, you're going to get at least 80% of the homework done with just that alone. And then all's going to be good. Have a good weekend. Today was the start of Ramadan as well. So I actually got it off when I was in Kazakhstan because it was a Muslim country, predominantly Muslim. So they actually gave us off. It's kind of nice. That's what I like about Thailand. They celebrate it just about everything. So from the Muslim, the Catholic, the Christian, the Buddhist, all the holidays.
I learned that chewing gum is not allowed
Oh.
during Ramadan.
Oh. It's good to know.
So one thing I had to write down is I know it's the second time around, but there was one thing I wasn't going to stop last time for this. But you multiplied this, and could you just go over?
Thank you.
You're welcome. Thank you.
How to do something? It is super simple, so please don't overthink my question.
No, so just think of this as 5/1.
That's it.
Yeah. And it's
Sorry.
the top and the bottom.
I knew what I was missing. I didn't want to stop.
Well, but it looked like what you were seeing is it looked like a mixed number the way they had it written. So
Yeah.
I don't like the way they got that
Because I
written.
wrote it down exactly
Yeah.
as.
Yeah. So it
You
looks like a
wrote it.
mixed number. Yeah.
And I'm going to let you know too that I have some family friends who are looking for interns over the summer in data analytics.
Uh-huh.
So I'm just figuring I would put that out there if you know of any students who are interested or looking for internships and possible jobs after.
Okay.
I don't really know anybody in data analysis in business.
Thank you.
But,
Thank you. Okay.
I just wanted to bring it to your
Thanks.
attention.
Thanks.
No problem.
I might. They follow up with me. I don't know if they're ready for an internship, but
Sure.
yeah,
I'll send
sure.
you the information that I have.
Perfect. Perfect.
Thank you.
Thanks.
Going back to the example we were working on earlier.
Do you have a quick question first?
Oh,
or-
no,
oh,
I can.
oh.
What did you get from this point when you said it's equal to 0?
Mhm. So
That point, because you,
right. So this was the derivative.
yeah.
So then to solve it is you subtract 0.001 from both sides.
To the side.
So that comes over here. So then you divide by negative 625. So that's this part here.
It's like from this, so you subtract that, so.
No, I divided by.
I know, but
Okay.
that's moving on to the other side.
Okay.
Like, we're moving,
There you go, yeah.
one.
And divide by that.
That is- Oh, okay,
Yeah, it's kind of,
yeah. I was just looking back at it, it was kind of messy there.
yeah, and then it's a x to the minus 2, so it's in the denominator.
Yeah.
That's why I just say just flip
Okay.
it.
Alright, thank you.
You're welcome.
So I emailed it, Tuesday, I was doing, I'm like a quiz exam. But I didn't see the email until after the exam, so I already expected her to
Okay, yeah.
And so I like took the exam.
Enjoy working.
Sure, like the whole time was really sick, and I was just going to ask if there's any like way I could take it in. If not, I completely understand. Like it's completely
Let's-
fine.
Yeah, let's see how we did.
Okay.
Maybe get the grading done. 'Cause
Okay.
that's basically what I say is if you can come,
Mhm.
come.
Yeah.
And it's, you can't come,
Mhm.
doesn't
Right,
matter.
yeah.
where it's go. So, yeah, and on the last day, it's kind of like, cause I'm from 7:30 in the morning in class.
Right,
So,
yeah.
but let's just see how it turns out.
Okay.
Like I said, I do look for increase
Mhm.
stuff, but if it makes sense, we do something.
Okay, thank you. I appreciate it. Have a good night.
Thank
Thank
you
you.
too.
I have a couple of questions about this.